Hello friends, good afternoon and welcome to EduSat Live Lectures. Dear friends, today in Thermodynamics we will be talking about Equilibrium Thermodynamics Properties Part 2. To discuss this topic we have with us our subject expert Dr. Amit Kumar. Dr. Kumar is Assistant Professor in Department of Chemistry in the Dayal Singh College, University of Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, sir.
Thank you so much. Dear viewers, let me first of all wish all of you a very good morning, very good afternoon rather to say. Friends, as you know, we had already covered a number of equilibrium properties in our previous lecture. So, we now switch on our attention to further implication of equilibrium properties of the thermodynamic systems. But before that, it becomes important to discuss one thing which has been left till the point of time. As you know, we had discussed the criteria for spontaneity and equilibrium for chemical reactions also. There we had discussed that there are four kinds of chemical reactions, as we could have classified them as in mainly the four different types. One which are universally always spontaneous, that is those reactions in which the entropy increases as well as the enthalpy of the reaction is a negative quantity, that is enthalpy change of the reaction is a negative quantity. So, in that sense Gibbs free energy of the reaction is a negative value, and therefore, as the reaction proceeds the Gibbs free energy of the reaction system to decrease, and as a result we have whatever the reaction we have envisaged is a spontaneous one. Coming over to enthalpy driven reactions, the reaction in which entropy of the reaction increases, that means delta Rs in this formula, as you can see, delta Rs, delta R system is a positive value, and T equilibrium is the equilibrium temperature at which the reaction is being started, and so therefore T delta S is a positive value, and with minus sign it becomes a negative value. So, now suppose if there is some reaction in which this delta Rs is a negative value, it means that in that reaction and entropy of the reaction system decreases. Then in that sense delta Rs will be a negative value, and negative when multiplied with the negative sign it becomes a positive quantity. So, therefore, in order to have Gibbs free energy of the reaction system to be a negative quantity, in order to have a spontaneous chemical reaction, it is only then. Now, the onus remains on the enthalpy change of the reaction system. That reaction has to be exothermic, and we always tend to keep saying that the reaction is exothermic, and it is the decrease in enthalpy of the reaction which drives the reaction, or in other words we can say the particular reaction is spontaneous because enthalpy decreases of the enthalpy of the reaction system decreases as the reaction proceeds. This is not a correct way of interpretation about the spontaneity of a chemical reaction. Why this is so? That is what I would like to highlight upon. You see, for this to be seen, let us rearrange this equation once again in a way that let us divide this equation delta Rg system equal to delta Rh system minus T equilibrium delta Rs system less than equal to 0 for a spontaneous reaction by equilibrium temperature TEQ. So, what we get is this equation delta Rg system by T equilibrium equal to delta Rh system by T equilibrium minus delta Rs system, because here the temperature gets cancelled. So, in the last term you have only delta Rs system here. Now, coming over to the situation, in this equation what is it written? It is written delta Rh system. Now, what is delta Rh system? Whatever the heat is either absorbed or is released by the reaction system, then the opposite effect will be observed in the surrounding. So, therefore, if delta Rh system is a positive value, then delta H surrounding will be a negative value. So, as a result, by way of this relationship, we instead of writing d delta Rh system, we can write minus delta Rh surrounding. So, now if a reaction is exothermic, what it does mean? Delta Rh system is a negative value, and therefore delta Rh surrounding would be what? Would be a positive value. So, in that sense you can say if delta Rh surrounding is a positive value, So, what is delta R at surrounding by T equilibrium? Isn't it the entropy change of surrounding? That is what we need to look at. That is minus delta R S surrounding minus delta R S system, that is less than equal to 0, which is equal to delta R G by T equilibrium. So, basically the Gibbs free energy of that reaction system decreases because the entropy change in the surrounding is much more as compared to entropy change within the system, and this accounts for the reaction being driven in the forward direction and so being spontaneous. It is not because the reaction occurs with an evolution of heat, that is enthalpy change is a negative quantity, or it is spontaneous because it occurs with decrease in enthalpy. It is not so, rather we should say that it is the entropy change in the surrounding which is a positive quantity and having greater magnitude compared to the entropy change within the system, and that actually makes the total entropy change of system and surrounding positive value, and that is how the reaction we can say is spontaneous, because on overall within the system and surrounding taken together the entropy always increases. That is how we should interpret it. Having said this, now we switch on our attention to thermodynamic equation of state. Once again have a look at one of the fundamental equation of thermodynamics, that is du equal to Tds minus Pdv. That results when we consider that the system is basically is not capable of doing any work other than work of expansion, and then in that situation work of expansion we can do substitute for P of dV, and when the whole system is in a undergoes the process which is a reversible process, then P opposing pressure would always be equal to the internal pressure, and that is how this equation was observed. Now, all we can do is we can divide this equation by dV and keep the temperature constant, that is under isothermal condition. So, what we get is delta U delta V constant T equal to T delta S delta V constant T minus P, because dV cancels there. So, which we can rearrange to get the pressure. What is it? It is the pressure of the system which is related to the temperature. The other is the delta P delta T and delta U delta V differential coefficients. So, basically isn't it the equation relates the state variables of system. So, we call this equation therefore as equation of state, and if you remember in our some of our previous lectures we had made use of this equation of state in order to derive various thermodynamic properties. So, there we had made use of these equation of state. Another equation of state also results when we consider second law of thermodynamics in its second fundamental equation, dH equal to TdS plus VdP. So, now we can divide, because H is there, H, let that H change in H, P and S be change at constant temperature, then we can divide with constant pressure, then all we can do is we can rearrange the equation. What we get is the volume of the system related to another side the temperature, the expansion coefficient and the Joule-Thomson coefficient. So, therefore, which has been an experimental property. So, therefore, all we can say is now we have a relationship between various thermodynamic state functions, state properties of the system. So, therefore, these equations, the equation 24 over here and 22 in the earlier slide, these are called as equation of state, and more important is the fact that these equation of states are explicable to the matter in each of its state, physical state or any state of aggregation. For example, in solid phase, in any of its allotropic modification, a gas phase or liquid phase, and so on and so forth. Right. So, once again let us consider the four different ways of looking at fundamental equation. The fundamental equation which we derived, the first one, that was du equal to Tds minus Pdv, as I just explained right now, as an implication of second law of thermodynamics, following which we can make use of modification in this equation in terms of change in enthalpy, Helmholtz energy and the Gibbs energy, and ultimately we have four different fundamental equations which are equation 2, 5, 8, 12 over here, which relate to the change in internal energy, the change in enthalpy, the change in Helmholtz energy and the change in Gibbs energy. So, these equations suggest us that internal energy is therefore is a function of entropy and volume. And enthalpy, what about enthalpy? Since enthalpy is related to change in entropy and pressure, so therefore enthalpy can be considered as function of entropy and pressure. That's in the same way Helmholtz energy can be considered as function of temperature and volume, and Gibbs energy as function of temperature and pressure. If these four fundamental equations suggest us which functions are related to which are the natural independent variables. For example, for internal energy, natural independent variables are entropy and volume. For enthalpy, the entropy pressure, the Helmholtz energy, the temperature volume, and Gibbs energy, the temperature pressure. So, we can make use of these definition of these functions in order to write the complete change in internal energy, total infinitesimal change in internal energy, that is du. This is equal to rate of change of internal energy with change in entropy at constant volume multiplied by the change in entropy of the system, plus now the next term is the contribution of volume change towards the internal energy change. So, for this we need to first of all write differential coefficient how energy changes with volume, that is delta U delta V at constant S, that is when entropy is kept constant. So, when we multiply this rate of change of internal energy with volume with the total change in volume, then what we get is the second term, that is the contribution of volume change towards the internal energy change of the system. So, in this manner we can determine how much the internal energy changes in this way. Now, coming over to enthalpy change. Now, this enthalpy change we can also look as dH. This is equal to rate of change of enthalpy with entropy at constant pressure times that entropy change plus delta H delta P, rate of change of enthalpy with pressure at constant entropy, and with that differential coefficient we need to multiply with change in pressure, and that allows us to determine how much is the enthalpy change due to pressure change alone. So, therefore, in the same manner Gibbs free energy then as also is a function of temperature and pressure. So, therefore, when we write rate of change of Gibbs free energy with temperature, that is delta G delta T at constant P into dt with total change in temperature, what we get is due to the temperature change how much the Gibbs free energy changes keeping the pressure of the system constant, and the second term, the rate of change of Gibbs free energy with pressure at constant temperature times dP actually determines the change in Gibbs free energy due to pressure change alone. Same way we can also interpret about the Helmholtz energy also. So, Helmholtz energy is also is a function of temperature and volume. So, there are two things which can change its value, the temperature change and the volume change. So, first term represents the quantified amount of change in Helmholtz energy, contribution towards the change in Helmholtz energy due to temperature change, that is we can determine by writing differential coefficient delta A delta V constant T, which is rate of change of Helmholtz energy with temperature times the total change in temperature. So, similarly, rate of change of Helmholtz energy with volume with total change in volume, that actually accounts for the change in Helmholtz energy. But now, most important, the fact of matter is why we are doing all this here is, if you see right hand side, these four equations are written. These four equations are basically representing the total change in total infinitesimal change in internal energy, enthalpy, Gibbs free energy, and Helmholtz energy. And also at the left hand side corner also, these four equations, these are four fundamental equations, also relates the same changes, the change in internal energy, the change in enthalpy, the change in Helmholtz energy, and the change in Gibbs energy. So, the point is that we can compare these equations, that is we can compare this first equation du equal to TdS minus PdV with du equal to delta U delta S constant V ds plus delta U delta V constant S dV. Similarly, we can compare dH equation also with this dH. Similarly, we can compare dA with dA and dG with dG. So, what results out of this comparison, basically that we need to understand. If we compare du equal to TdS minus PdV equation with du equal to delta U delta S constant V ds plus delta U delta V constant S dV. So, in this equation, if we compare these two equations, if you see very carefully, the differentials ds and dV are the same in both these equations. What changes is that differential coefficients. Here is partial differential coefficient delta U delta S constant V. So, it should be compared to the temperature. So, therefore, this is how we can say, as a comparison of these two equations, we can say delta U delta S constant V is equal to temperature. And similar comparison can also be made between the differential coefficient of volume differential, that is, this is the differential coefficient for this small change dV. So, this differential coefficient can be compared to volume there, sorry, this is H, that is, yeah. So, this is dV, here du equal to dV here minus P dV. So, dV is the differential which is common to both these equations. So, therefore, the differential coefficient delta u delta V constant S is actually equal to minus P. So, therefore, this is what we get. So, in at the left hand side, if you see the two differential coefficients which are written and are related to one state variable, they actually help us to determine how the internal energy changes with change in entropy under isochoric condition. For any system which is maintained at a fixed temperature, for which if entropy increases, then since temperature is a positive value, so internal energy will also lead to an increase if the volume of the system is kept constant. So, it means both the internal energy and entropies are varying linearly. As entropy increases, it also leads to an increase in entropy simultaneously if the volume of the system is kept constant, and greater is the temperature of the system, greater increase will be observed. That is what is the meaning. So, it does mean that if you increase temperature, if you increase an entropy at a particular temperature, at higher the temperature, greater will be increase in internal energy. Similar interpretation can also be talked about by delta u delta V at constant S equal to minus P. Here you can see, if you rearrange the equation, this equation there at the which is written at the bottom left corner. So, this represents the change in internal energy with change in volume. As you can see, differential coefficient is minus P. So, P is a positive quantity, when multiplied with minus sign it is therefore a negative quantity. So, as the volume gets increased, the internal energy will also decreases, therefore, rather than an increase, internal energy here will decrease under condition of constant entropy. So, these interpretations are very helpful in order to understand what way a particular thermodynamic function or property will change as a result of change in other thermodynamic state variables or functions. Now, let us make interpretation about dH, the enthalpy change. dH equal to TdS plus VdP here. This is the second fundamental equation of thermodynamics, and therefore, here at the right hand side, because we had considered that enthalpy is a function of entropy and pressure, then we had written this differential equation for an enthalpy change. So, we can compare this equation, second equation, with this equation. So, what we get is the value of these differential coefficient delta H delta S constant P equal to T here, because T is the differential coefficient with ds, and here dP is written, its differential coefficient delta H delta P delta S should have its value, can be compared to volume of system, because here also we have dP. So, this suggests that under condition of constant entropy, when you increase at constant pressure, when you increase the entropy of system under condition of constant pressure, the enthalpy would increase, and when you keep the entropy constant and you tend to increase the pressure of the system, it will also raise the enthalpy of the system. So, that is what as an implication we can come to understand from these differential coefficient values. Now, the important one comes now. Why it is important, whatever we are going to discuss is that we are now going to see how the Helmholtz energy changes with change in temperature. As you could see, we had given a concept of free energy, where we have said free energy means energy which is available for its conversion into useful work. So, basically here also dA equal to minus SdT minus PdV, which is again a fundamental equation which can now be compared to this differential equation which we have just written. It suggests us that delta A delta T constant V equal to minus S, and similarly delta A delta V constant T equal to minus P. What it suggests is, and since entropy will always be a positive quantity because it always increases with temperature. So, therefore, we can take this dt to the right hand side, therefore, dA equal to minus S dt, at constant V volume. So, it means if the volume of the system is kept constant, when you increase the temperature of the system, Helmholtz energy will decrease. What is Helmholtz energy? It is A equal to U minus Ts. So, as you increase the temperature, it means T delta S factor would increase more than that of increase in just the internal energy. So, it does straight away means that as temperature increases under constant volume condition, entropy, since it increases, so therefore, it leads to a greater decrease in Helmholtz energy. So, therefore, at a higher temperature, system will be having lesser free energy for its available free energy per mole for its as its availability for its conversion into useful processes and products and useful work. Now, same interpretation can also be talked about when a system undergo expansion under condition of constant temperature. Now, what happens in that situation is, as this equation suggests that dV, if we take it to the right hand side, it means dA equal to minus P dV. Then when the volume increases, it means whenever the system undergo expansion, dV is greater than 0, a positive quantity, and multiply with pressure, which is a positive quantity, and multiply with negative sign means dA is a negative quantity. That is, Helmholtz energy of the system will decrease as the volume do increase. Why it is so? When the volume increases, there is the, because as you could see from the interpretation of statistical interpretation of entropy, we had seen that as volume increases, the entropy increases. Since entropy increases, the factor T delta S factor would also increase in its magnitude. So, there will be again the lesser out of the total energy, lesser total energy will be, a lesser portion of it will be available at higher volume at constant temperature for its conversion into useful work. So, that is the reason free energy gets decreased. Same interpretation you can look about this Gibbs free energy, but here is one important, very important and valid point. Again, as temperature rises under condition of constant pressure, the differential coefficient delta G delta T constant P equal to minus S do suggest us that the Gibbs free energy decreases with increase in temperature, and the decrease, more important, is more for a system which has greater entropy. Now, this equation has very important kind of implications. We will come to understand what are those implications. For the time being, let us consider another differential coefficient, that is delta G delta P constant T, which is equal to V volume. So, we can rearrange again. So, dG equal to V dP at constant temperature. What it does mean? If you keep the temperature constant, if you increase the pressure, how the pressure would increase? The volume will decrease. So, that is how you will decrease the increase the pressure. When pressure will increase, the Gibbs free energy will increase. So, Gibbs free energy is therefore a measure of pressure of the system. It clearly indicates, as pressure increases, Gibbs free energy increases. If pressure decreases, then Gibbs free energy of the system will decrease, and the decrease is more for that kind of a system which has greater volume. It means, if we compare the same substance, for example, water in liquid phase and water in solid phase. In solid phase, water has lesser density. The volume occupied by just 1 mole of water is more in solid phase. So, if volume is more, so it means when you apply greater, if you subject the water in solid state, that is ice, is subjected to higher pressure, then its Gibbs free energy will increase more than when you increase the pressure of on liquid water with the same value. Then the Gibbs free energy would also increase, but the increase would not be as much as it will be on solid water, because the volume occupied by just 1 mole of water in solid phase would be more there in that state. So, therefore, as I said, this has important implication. This we can see clearly from here. You see, if temperature is kept constant, when temperature is kept constant, then dT is 0. So, what we have is dG equal to VdP, and therefore, dG equal to VdP means when pressure increases, so the Gibbs free energy will also increase. But now coming over to the point, which physical state, in which physical state a particular substance has greatest volume. It is the gaseous phase for which the volume is very high, that is being occupied by just same amount of substance, that is 1 mole. So, molar volume of in the gas phase is very high. As a result, you can see the change in Gibbs free energy is much more in the gas phase, as you could see from this exponential graph here. The Gibbs free energy of the reaction gases system, it increases continuously and there is a very sharp increase, and then thereafter it undergoes saturation at some point later. Coming over to liquids phase, the Gibbs free energy increases, but increases linearly over here, but to some extent a little increase is there. But for solids, the entropy, the Gibbs free energy almost remains same, is increases but only very slightly. So, therefore, we can say that for solids and liquids, that is condensed phase systems, since their molar volume occupied by 1 mole of the substance is compared to gas phase is very small. So, therefore, what you will do observe is, as a result of change in pressure, the Gibbs free energy of the system will change much more for the gaseous system compared to the condensed phase systems such as liquids and solids. And this is an indicative diagram which clearly suggests us that whatever the change in Gibbs free energy we observe as a result of change in pressure under constant temperature condition is much more for gaseous systems as compared to liquids and solids. This curve and this has implication, this has very important implication. So, what it does mean, if the Gibbs free energy, here we are looking at how Gibbs free energy changes with pressure, it does mean that the Gibbs free energy of a substance in condensed phase system almost remains same with that of pressure, that does not change much unless the pressure changes very high. So, therefore, for working in usual comparable range of pressure, it means Gibbs free energy is practically a function of temperature only for condensed phase systems. However, Gibbs free energy will be a function and will vary significantly with pressure for gaseous systems. That is what we interpret from this differential coefficient value, right. Having said this, now it is time to understand that what is the what happens to the Gibbs free energy of a substance in different phases as you subject it to a change in temperature. So, what this relationship, the differential coefficient delta G delta T constant P equal to minus S suggests to us, since entropy is a positive quantity. So, del dG equal to minus S dt at constant pressure. So, it means under constant pressure condition, the Gibbs free energy of the reaction system will decrease and decrease with increase in temperature, and the decrease will be more for such a system or substance for which entropy is having a greatest value. Now, coming over to the point in the towards the for the discussion, keeping the discussion of previous lectures in mind, that we had said that molar entropy of a gaseous substance is much higher compared to molar entropy of liquids, which are higher than that of molar entropy of solids. So, what it does mean? It does mean that the differential coefficient delta G by delta T at constant P equal to minus S will be having a greater negative value for gas phase compared to liquid phase, and for liquids also this will be greater than that of the solids. So, what it does mean? It does mean that this interpretation can be looked at in the form of a graph. You see, here we can see that the Gibbs free energy for the gas phase having a greatest slope. It means Gibbs free energy decreases very sharply with gases. This is a clear implication of this formula delta G by delta T equal to minus S. That is, if because the molar entropy for gaseous system is highest compared to all the three, then in that sense it means that the Gibbs free energy will decrease more in the case of gases, and that is very clearly shown in the graph over here. it is the graph between Gibbs free energy and temperature, and dG by dt is the slope of this curve, and this dG by dt, the slope as you can see is greatest for the gases system. So we will also now discuss the change in Gibbs free energy for liquid and solid systems, to be discussed shortly. Right, dear viewers, in this session we now switch on our attention towards the change in Gibbs free energy of the reaction system with change in temperature. As you could see, this is again related to this differential coefficient S. Now, since the molar entropy of liquids are lesser, so you could see the slope for the dG by dt, which is the slope for G versus T curve, is lesser as compared to the curve for gaseous system, and this is being having a higher slope compared to the solids. Now, it is important to understand, it means that Gibbs free energy for the gases decreases very sharply with increase in temperature. On the other hand, Gibbs free energy also decreases with temperature for the liquids and solids, but the decrease is not as sharp as for gases. Now, having said this, now let us have a look at a numerical factor. But before that, it is important to understand, if we consider that an ideal gas which undergoes an isothermal reversible expansion, then we need to show that the change in Gibbs free energy equal to its Helmholtz free energy, change in Helmholtz free energy also. What is Gibbs free energy function G, which is equal to H minus Ts, and what is A, the Helmholtz free energy, which is equal to U minus Ts. Both these equations are important in different conditions, that is temperature pressure and temperature volume being kept. When we consider temperature pressure constant, G becomes important to be considered, and A becomes important to be considered when volume is kept, temperature volume is kept constant. The function H is given by H equal to U plus PV, so which we can substitute in the equation for G equal to U plus PV and minus Ts, and now which we can rearrange here U minus Ts plus PV. So, G equal to A plus PV. Now, we can write for a finite change that Gibbs free energy therefore is equal to change in Helmholtz energy plus change in pressure volume. Now, what is this PV? If this we are considering the ideal gas which undergo isothermal expansion. So, therefore, for an ideal gas equation, for an ideal gas there is an ideal gas equation according to which, according to this P v equal to nRT. So, we can substitute nRT for P v. What we get is delta P v equal to delta nRT. Now, n, that is initial number of moles. Once we take since we have already said in the for thermodynamic purpose we always are going to take constant composition systems, therefore, the number of moles are not going to change. So, n kept constant. So, you can take it outside of delta, R is gas constant, you can take it outside delta, and therefore, delta T. Now, delta T under isothermal condition. So, therefore, temperature remain constant, delta T equal to 0. So, therefore, delta P v equal to 0. So, that if delta P v equal to 0, it means this means that delta G equal to delta A. So, this is an implication we should understand, that for isothermal processes which are that is specifically the reversible expansion of an ideal gas under isothermal conditions, the change in Gibbs free energy equal to the change in Helmholtz energy. This is because there is this P v factor, the temperature remains same. Right. Having said this, now for a chemical reaction, if we want to quantify the change in Gibbs free energy, now as we all know, the standard reaction Gibbs free energy equal to summation nu b standard Gibbs free molar Gibbs free energy of all the reactants and products, and the sign of nu takes care of being positive for products and negative for reactants. So, it is therefore become a change, the finite change, and that is how delta R A equal to nu b del A m standard b. Now, G equal to A plus P v. So, therefore, G m standard equal to A m standard plus P v m. Now, with this delta R G is becomes what, summation nu b G m b, and instead of G m b standard you can put A m standard b plus P v m. Now, instead of P v m you can put R T, because for 1 mole of an ideal gas P v m R T. So, therefore, when you put in R T there, you can take, since R is constant, will not vary on a counter, temperature will not vary on counter, you can take it outside, summation nu b therefore is delta nu G, because nu is having plus sign for products and negative minus sign for reactants, and G is being written over here because we are going to consider only the reaction systems which only those chemical species in the reaction system which are gaseous in nature, because for all others it does not figures in, we have already discussed in our previous lecture. So, therefore, delta R G standard equal to delta R A standard plus delta nu G R T. So, this is our formula to calculate Helmholtz free energy. Now, we can consider a numerical over here. Now, the question is that delta R G for a reaction is given, this particular reaction, which is nothing but the combustion of benzene. So, therefore, it asks us what would be its Helmholtz energy. So, it straight away the change in stoichiometric coefficient for this balanced chemical equation we can consider. As you can see, water occurs in liquid phase in the product side, we will not consider its stoichiometric coefficient. For that purpose, therefore, carbon dioxide in gas phase, oxygen in gas phase. So, therefore, 6 minus 7 and half for oxygen equal to minus 1 by 2 is the delta nu G. So, delta R G standard by way its formula, delta R A standard equal to delta R G standard minus delta nu G R T, and delta nu G we have seen that is minus 1, right, 1 by 2, 3 by 2 therefore, which we can substitute 1.5 into R into T, and that is 8.314 joule per Kelvin per mole and 298 Kelvin. Delta nu G is dimensionless, and therefore, and here this is delta R G standard, and therefore, we ultimately get is delta R A standard, that amounts to 3.1983 megajoule per mole, megajoule per mole, because 10 raised to the power 6 is been there, that has been accounted for. So, now it is time to see how the Gibbs energy changes with change in pressure. Now, let us see that volume is related to pressure through the ideal gas equation, V equal to nRT by P, we all know this. Now, if we substitute in equation, which equation is, just see that in order to have a variation of Gibbs free energy of with pressure, what we need to do is we need to consider the differential coefficient delta G by delta P under constant temperature condition at T, constant T equal to V. Now, which we can rearrange this equation dG equal to VdP at constant temperature. Now, when we integrate this equation within limits P1 to P2, we get from P1 to P2 dg equal to integral P1 P2 V dP. Now, when we integrate this left hand side G2 minus G1, that is in final minus initial, equal to V into P2 minus P1. Here we have made one assumption, V is constant within pressure range P1 to P2, and this is practically true for condensed phase systems. Since for condensed phase systems volume does not change much with the pressure, so we have considered that within pressure range P1 to P2 volume does not change much. So, therefore, G2 minus G1 equal to V into P2 minus P1. More important is the fact that molar volume for condensed phase systems is very small. So, therefore, this small value when multiplied with small change in pressure P2 minus P1, there will be a very negligible quantity. So, we can say G2 minus G1, which is the difference in Gibbs free energy due to pressure change, would be a very insignificant value, insignificant quantity, very negligible quantity. So, therefore, we can say for condensed phase systems Gibbs free energy is a function of temperature only. This is an important implication of the differential coefficient delta G delta P at constant T equal to V. Now, as usual, we have been observing that for gaseous systems this value will be changing in significantly. So, therefore, for an ideal gas, suppose we have we can make use of ideal gas equation to determine volume V equal to nRT by P, and in the equation this one, that is that dg P1 P2 which is equal to G2 minus G1, when we integrate it P1 to P2 V dP, instead of V dP we can put nRT by P. So, dP by P we can integrate, and keeping the nRT constant and outside of this integral, and therefore, for one mole of for an ideal gas we get delta G equal to G2 minus G1, that is the Gibbs free energy of an ideal gas at a pressure P2 minus Gibbs free energy of an ideal gas at a pressure P1 equal to nRT ln P2 by P1. Making use of ideal gas equation, again we can convert in this P1 by P2 with V1 by V2. So, these are two equivalent equations which suggest us that the Gibbs free energy for an ideal gas changes by this much value for a particular change in pressure or change in volume. And moreover, we have seen that with increase in pressure the Gibbs free energy of the system increases, and with change in volume the Gibbs free energy of the system decreases. That is why you could see that P2 by P1 which has been there, the P2 being higher as over here in volume change, V1 is initial volume and V2 is final volume, and as volume increases this V2 is higher. So, therefore, this fraction will be lesser than 1, and therefore, this value will be a negative value. Right. On the basis of this, let us consider a numerical portion over here also. Calculate Gibbs free energy for the conversion of 3 mole of liquid benzene at 80 degrees Celsius, that is its normal boiling point, to vapor at same temperature at a different pressure. So, it means first of all this conversion is that benzene at 80 degrees Celsius in liquid phase at 1 bar pressure converts to benzene in gas phase at 80 degrees Celsius and 0.66 bar pressure. So, therefore, in this transformation there are two changes which are being carried out, which are being done. One is the phase transformation, other is the pressure change. So, therefore, we need to split the process in two steps. Step 1, in which 3 mole of liquid benzene undergo transformation reversibly to 3 mole of benzene in vapor phase at 1 bar pressure at 80 degrees Celsius, same temperature. So, for which, since this phase transformation is reversible in nature, for all reversible processes, which therefore we consider as condition of reversibility at condition of equilibrium, and for an equilibrium delta G equal to 0. So, therefore, any reversible transformation of the system delta G is equal to 0. It means for the phase transition from liquid phase to benzene in vapor phase, this delta G is equal to 0. And when the same 3 mole of benzene therefore now convert in vapor phase to again in the same vapor phase, but at lower pressure, for this you can calculate the change in Gibbs free energy delta G equal to nRT ln P2 by P1. So, P2 is the lower pressure and P1 is the higher pressure. So, that is how you can see this fraction will be a negative one and therefore, delta G will be a negative value. So, in this way we can split such processes in all steps. We should consider whenever a numerical comes to be solved, we should understand what is an overall process which is undergoing, for which or the transformation for which a change in or value of or change in different quantities are required. So, we should, once we have written that process or transformation in one overall, then we should split it considering which formula can be made use of in order to have those split values be calculated and added together to get total Gibbs free energy change. So, Gibbs free energy change step 1 and step 2 therefore equal to Gibbs free energy change for overall transformation of benzene in liquid phase to vapor phase at same temperature 80 degree, but at a lower pressure. So, that is how you can calculate all numerical problems also you can address. Now, in order to have standard Gibbs free energy of a reaction system, we require standard Gibbs free energy of substances. So, what was standard free energy of a substance at a given temperature is the free energy of the substance at 1 bar pressure. The free energy of an ideal gas at a pressure P relative to standard Gibbs free energy can be obtained as delta G equal to nRT ln V2 by V1, which we have seen just right now. Similarly, free energy of an ideal gas at a pressure P relative to standard Gibbs free energy can be obtained as G2 minus G1. Now, what we have done is we have made use of a formula. Which formula? Just have a look at. We had made use of this formula del G2 minus G1, that is G2 at the value of Gibbs free energy at one pressure minus value of Gibbs free energy at other pressure. If G1 is the value of Gibbs free energy under standard pressure that is 1 bar, then this equal to nRT ln P2 by P1 is 1 bar. So, therefore, G2 we can make we can put it as such, we can say G2 as G, that is Gibbs free energy at temperature P and at pressure P. Now, if you want to calculate it relative to standard Gibbs free energy, then G1, because P1 is 1 bar, then G1 becomes G standard. So, G2 become GTP and G1 become G standard T, which is equal to nRT ln P2. Instead of P2 you can just write whatever is the value of P2, that let us say P, and divide by P1, which is in each because relative to standard pressure you are going to determine. So, P1 is 1 bar. So, which you can take this G standard T to right side. So, GTP equal to G standard T plus nRT ln P by 1 bar. So, basically what we are trying to say is that Gibbs free energy at temperature T and at pressure P can be determined relative to Gibbs free energy, relative to standard Gibbs free energy, that is equal to standard Gibbs free energy at same temperature T plus nRT ln P by 1 bar, that is this is P divided by 1 bar means pressure in bar unit is divided by 1 bar, means this is dimensionless quantity, and logarithmic of anything which we have to take is dimensionless quantity. So, therefore, it is important to note that Gibbs free energy of any system at temperature T and pressure P is related to its standard Gibbs free energy and with a factor nRT ln P by 1 bar. So, therefore, as from this equation you can easily see, as the pressure will increase, so the Gibbs free energy of the reaction will of any substance will increase. It means Gibbs free energy is a measure of pressure of the system. So, therefore, now when we divide by total number of moles, then what we get is G divided by N equal to G standard by N plus RT, N gets cancelled with N, ln P by 1 bar. Now, the fact is if you could see in other next equation we have written GTP by N as mu. Mu is called the chemical potential, and therefore, G standard by N is mu standard, the standard chemical potential plus RT ln P by 1 bar. So, chemical potential is the free energy per mole of a substance, that is it, nothing else, but chemical potential is a very important quantity in thermodynamics to deal with. So, therefore, chemical potential basically is a function of temperature and pressure, and as the pressure increases the chemical potential value increases. So, therefore, chemical potential is a measure of pressure of the system, and therefore, chemical potential at a temperature T and pressure P can be related to standard chemical potential plus the higher pressure term RT ln P by 1 bar. Right. So, with all this discussion, which the pressure dependence of Gibbs free energy has helped us to calculate the chemical, to make an important concept called chemical potential. Now, let us see how the Gibbs temperature dependence of Gibbs free energy, how the Gibbs free energy changes with change in temperature, and what this equation has an important implication for us. The change in free energy with change in with temperature at constant pressure is given by differential coefficient delta G delta T constant P equal to minus S. Now, the fact of matter is that is G equal to H minus Ts, which you can rearrange. How? Is very simple. G equal to H minus Ts, so H you can take it to left side, G minus H. Now, you can divide by T equal to minus S. So, the definition, by definition, the Gibbs free energy equal to H minus Ts, this equation you can rearrange to determine minus S equal to G minus H by T. So, therefore, the first equation G by T del G by del T at constant P equal to minus S, second equation minus S equal to G minus H by T, you can compare the two equation, and what you get, del G by del T at constant P equal to G minus H by T. Or now you can further rearrange this equation, you can take this T to the left hand side, you can multiply T with and differential coefficient, what you, and then you can take enthalpy to the left side, what you get, G equal to H plus T into del G by del T at constant P. Now, for a chemical reaction, the same equation modifies to del G by del T, instead of del G by del T, we can write del delta R G by del T at constant P. So, which is equal to delta R S. If you remember, del G by del T at constant P equal to S minus S. So, del of delta R G by delta P at constant P equal to minus delta R S, and now this minus delta R S is equal to delta R G minus delta R H by T, which we can rearrange, and then what we get is delta R G equal to delta R H plus T into del of delta R G by del T at constant P. So, what this equation is? This equation is called Gibbs-Helmholtz equation, and why this Gibbs-Helmholtz equation is an important one, that we need to understand. You see, if you look at the equation, what it relates to, it relates the Gibbs free energy of the reaction system with the enthalpy of the reaction plus T and the rate of change of Gibbs free energy with temperature at constant pressure. Now, having said this, now let us once again consider this Gibbs-Helmholtz equation, that is delta R G by T equal to delta R H. You see, it is a different thing now. Delta R G equal to what? Equal to delta R H minus T delta R S. So, delta R G by T equal to delta R H minus T delta R S by T. So, which we can open, and what we get is delta R H by T first term minus delta R S, T cancel in both numerator and denominator. So, therefore, what we get, delta R G by T equal to delta R H by T minus delta R S. Now, so what we get is delta R G by T, and we know from our observation from Gibbs-Helmholtz equation that delta R G equal to delta R H plus T delta R G by del T. Here we can substitute the value of delta R G in this equation, and therefore, it means we can quantify del delta R G by T by del T, as you could see this one. So, when we substitute here this delta R G by T value, what we get is the two factors. One is differentiation of delta R H by T with temperature at constant pressure. The second is differential of delta R S with temperature at constant pressure. So, therefore, now we need to differentiate it. and since you see in the first term delta differentiation is of delta RH by T. So, we can split it as a product of two functions. Delta RH also is function of temperature, temperature is of course a variable which needs to vary with temperature. So, therefore, we can consider 1 by T as one function, delta RH other function. So, let us keep the first function delta RH as such and differentiate the second one T 1 by T, differentiation of 1 by T minus 1 by T square, then plus, then we can write 1 by T and then we can multiply with the differentiation of second function delta RH. So, delta RH by delta T at constant P, then minus this one is simple, delta of delta RS by delta T at constant P. So, now we need to understand what this del H by del T at constant P is. What is del H by del T at constant P? This is nothing but the heat capacity. So, del of delta RH by delta T at constant P therefore should be difference of difference of heat capacities of products and the reactants. So, therefore, the second term is delta R Cp by T. Moreover, this last term del of delta R S by delta T at constant P is again from the entropy considerations. If you remember, entropy as a function of temperature and pressure we had when we had discussed, we also had coined that this differential coefficient is nothing but delta R Cp by T. So, therefore, the two are same, but with different sign. Now, the first term, coming over to first term, minus 1 by T square delta RH is as such you can note. So, therefore, minus delta RH by T square plus delta R Cp by T minus delta R Cp by T. So, second and third term are same, have same magnitude but opposite sign. So, therefore, they do cancel. What we get is minus delta RH by T square. So, therefore, we have another form of Gibbs-Helmholtz equation which says that del change in ratio of reaction Gibbs free energy to temperature with change in temperature equal to minus delta RH by T square. Now, which we can rearrange it. We can take this minus 1 by T square to the denominator of the left hand side, and now we need to understand is differential of 1 by T equal to minus 1 by T square dt. So, therefore, in this equation second minus 1 by T square dt, instead of this you can write del of 1 by T. So, del delta Rg by T by del 1 by T equal to delta RH. So, this is the other form of Gibbs-Helmholtz equation. If this delta RH is independent of temperature, what we can make use of, we can draw a plot between delta Rg by T versus 1 by T. It will give a straight line, and this the equation suggests, and then therefore, with slope that should be equal to delta RH. So, we can determine in this way the enthalpy change of various reactions. That is, we can just calculate the Gibbs free energy change of reaction by temperature with inverse over temperature, and we can calculate delta RH enthalpy of reaction from the slope values. So, delta RH depends on temperature, then slope value also needs to be calculated making use of Kirchhoff's relations. So, that way we can say these quantification of Helmholtz Gibbs free energy and enthalpy of reaction can be done. So, with this we come to the conclusion of equilibrium properties of thermodynamic systems and the reaction systems. So, following which any subsequent discussion when will be devoted to, this will be devoted to straight away for the discussion of systems with variable compositions. So, till the point of time at a glance we can say we have considered only systems which have a constant composition, and we have conceptualized various state functions of system, on the basis of which we have predicted whether the changes we envisage in our reaction system or any other physical system, those changes will be spontaneous or not. That is what is the job of chemical thermodynamics, and that is what we have been able to complete. But now on we need to see what way we will deal with systems with variable compositions. So, with this we do come to the conclusion of chemical thermodynamics for systems with constant compositions. So, any discussion which now will be devoted to thermodynamics of chemical systems with variable compositions. So, with that we will devote our discussion in our subsequent lectures. Thank you so much.
On that note, I would like to thank Sir for this very enriching discussion, and I would like to thank you, dear friends, for watching our show. Stay tuned and keep watching. Thank you.